Torque on a current carrying bar. A uniform bar of length capital L carries a current I in the direction from point A to point B. So this is the direction of the current. The bar is in a uniform magnetic field that is directed into the page. Consider the torque about an axis perpendicular to the bar at point A that is due to the force that the magnetic field exerts on the bar. Part A, suppose that an infinitesimal section of the bar has length dx, this part, and is located at distance x from point A. Calculate the torque d tau about point A due to the magnetic force on this infinitesimal section. Okay, so let's put our x-axis here, y-axis here, so that the z-axis is coming out of the page, and our infinitesimal section is has a width dx and it's at a distance x from point A. So if I write the force acting on it, I can basically first of all note that the dl vector here, because the current is in plus I hat direction, is the width dx in I hat direction. The magnetic field B is into the page, but the positive z axis is coming out of the page. So it is B in minus k hat direction. So if I write the torque, the force acting on this line element, it's I dl vector cross product with the magnetic field vector, and that is equal to I dx I hat cross with B in minus k hat direction. So what is I hat cross k hat? So you can see here, using cyclic permutations, I hat cross j hat is k hat, j hat cross k hat is I hat, k hat cross I hat is j hat. So if I write I hat cross k hat, because this is the positive direction, I'm going in the negative direction, I hat cross k hat, that will give me a minus sign, so minus j hat. I hat cross k hat is minus j hat. On the other hand, I hat cross with minus k hat will be equal to plus j hat. All right, so this I can see from the cyclic permutations. So the answer is plus j hat. Therefore, the df is equal to I b dx in plus j hat direction. What is the torque d tau due to this force? It is the position vector of the line element with respect to the pivot point, cross product with the force r cross df. Now, what is the position vector of the line element? It is located at a distance x from point A. So it's going to be x I hat. X I hat, it's on the positive x-axis. So we see that x I hat cross product with df, which is IB dx j hat, will give me the torque. Now, what is I hat cross j hat? I hat cross j hat is k hat, that's the positive direction. So this gives me d tau vector to be IB, so this is the cross product here, IB x dx k hat. That's the torque acting on the line element. So I just need to be careful here. This is not x, it's the cross product. Okay. Now we have the answer to part A. Let's look at part B. use tau equals integral a to b d tau to calculate the total torque on the bar. Okay, so for each line element, I will have a torque in plus k hat direction. So I can just add them up to find the total torque acting on this bar in part B. The total torque, tau, will be equal to the integral from a to b d tau, and that is the integral from a to b I b x dx in k hat direction. The integral of x dx is x squared over 2, so I will have I b x squared over 2 in k hat direction, which will be evaluated between point A and point B. And point A basically means x is equal to 0. Point B means x is equal to L. So this is basically going to give me the final answer for the torque. Torque is equal to IB over 2 L squared in k hat direction. So that will be the total torque. So part C, show that tau is the same as though all of the magnetic force acted at the midpoint of the bar. If all the force acts on the midpoint of the bar. Okay. So the force is, magnetic force is equal to I L cross B. Now this is I L I hat cross with magnetic field in minus k hat direction. So the force is I L B. Once again, I hat cross k hat is minus j hat. I hat cross minus k hat is j hat. So this is going to be ILB in j hat direction. The torque is acting at the midpoint, so it is R cross F. Now R is L over 2 I hat, that's the midpoint, cross with ILB j hat. So that gives me the total torque to be I B divided by 2, and you can see I have two L's here. IB divided by 2 L square in k hat direction. That is the torque. Now this is the same result as part B. Therefore, this checks. So we can indeed say that we have the same result, and therefore the torque can be calculated by considering all of the force acting on the midpoint of the bar. Okay, so we're calculating the torque on a current carrying bar. First, we started with an infinitesimal element and we calculated the force acting on this element, which is I dl cross B. dl vector is in the direction of the current and it has magnitude dx, so I dx I hat. Magnetic field is in minus k hat direction because I've assumed the z-axis is coming out. So I hat cross minus k hat is j hat, so IB dx j hat. The torque is R cross df. R is the position vector of the line element with respect to the pivot point. It is x I hat, cross product with IB dx j hat. That gives me IB x dx k hat. I hat cross j hat is k hat. If I integrate this from x equals 0 to x equals L, IB x dx k hat, that gives me IB x squared over 2. and the distance between point B and A is L, so IB L squared over 2. If I assume all the force acts on the midpoint, the position vector of the midpoint is then going to be L over 2. The total force is IL cross B, which is ILB J hat. So R cross F gives me the total torque IB over 2L squared K hat, which is the same result as in part B. So this is true. The tau is the same as though all of the magnetic force acted at the midpoint of the bar.